Okay, I guess I'm back this week looking at 5 problems. So let's get to it. The first problem. So again, I'm not really going to spend too much time talking about the problem statement. I assume that you can read that instead of watching me talk about it. But anyway, the point is that you have a circle with 28 spots. Each spot has a letter of the alphabet A to Z. And then there are 2 extra spots, one for a space character and one for a single quotation mark. And you're going to be given a certain string, right? And then you have to start from the first letter and you have to run to the next letter and you just keep on hitting all the letters one at a time. And then you stop at each letter in the sentence to pick up something. And um, Joe wants you to write a program to estimate the expected time for one smart player to complete each of the algorithms. Assume that the player runs at 15 feet per second and pickup takes 1 second. Okay, so there are up to 20 cases and et cetera, et cetera. Um, you also told that this circle has a diameter of 60 feet. Okay, so that's the setup. Um, So basically, what you have to do is just follow um, the sentence. With the only thing that you have to worry about, of course, is you have a circle. So there are basically 2 ways to go if you want to get to a certain uh, from one place to the next. And so you have a circle. You have it doesn't really matter whether it's clockwise, counterclockwise, all the way up to here, X, Y, Z, and then space, and then single quotation. Exactly 28 spots. So if your sentence, I don't know, um, it's let's say A, C, E, X. Okay. So from A to C, this is the shortest way. So you have to go 2 spots, 2 spots. But now with E to X, you can decide to go this way, or you can also decide to go this way. Actually, even with A to C, there are always 2 ways you can go. Of course, in the case of A to C, it's obvious that it's better to go clockwise and counterclockwise, but there's no such thing as obvious when I write a computer program. So the question is, how do you figure this out, right? So it's just basically a modular arithmetic, if you want to call it that way. You can label these things all from 0 to 27. And if you want to go from a position to one position to another, so E to X, for example, so E is 4, X is 23, you have 2 ways. If you go E to X, then it's 23 minus 4 steps, which is 19, a lot. If you want to go the other way, X to E, it's 4 minus 23, which is minus 19, but you can't go minus 19. And now you have to remember that this circle has 28 steps. So if you're using modular arithmetic, if you take everything mod 28, now you have to remember what it means for negative numbers to be to do things mod 28. And actually, for one way to do it is to just say 28 minus 19, which is 9. So this, I guess, technically is 3 bars, congruent. So 4 minus 23 is actually 9 mod 28. So it's actually faster to go this way in 9 steps. Okay, so that's basically the first part is to figure out how many steps you have to go, right? So you can go 9 steps. So here you have to go 2 steps, 2 steps, 9 steps. So altogether you do, in this case, 13 steps. So you can add up all these steps. After that, you have to figure out, well, how much are these steps worth, right? So what's the distance? Because you want to figure out the time, so you know the speed. So you know the speed is 15 feet per second. So you want to know the time is something second. So you need to know distance is something feet, right? Once you have that, then time, it's distance divided by speed. Okay, so this is, I don't know when, I guess I learned this in high school physics. I don't know when people learn this. Anyhow, distance divided by speed. So if you want time, you need distance. Speed is given. So distance is how far you have to travel. I know that I have to travel a certain number of steps, but steps, it's not distance. So we have to figure out how much is one step worth. What's the distance, right? So the distance is basically you look at the circumference of the circle and divide it by 28 because there are 28 steps. So circumference of circle, again, you have to remember geometry. It's diameter times pi, right? So diameter, they tell you 60 feet. And pi, of course, is 3.1415, blah, blah, blah. But the easiest thing to do, actually, if you don't want to remember all of that, is actually arc cos of minus 1.0. So if you look at the unit circle, minus 1.0 is here. And then this theta is exactly pi, 180 degrees. And this is the cosine. So cosine of pi is exactly minus 1.0. So the inverse cos of minus 1 is pi. And you basically make C++ compute pi for you. It'll be more accurate than probably what we want to remember anyway. So instead of typing whatever number of digits you can remember, just do this. Okay, so if the circumference is 60 times pi, then each step is basically 60 times pi divided by 28. And then you multiply by a number of steps, that's how far you have to go. So that's basically what you have to do. So let me just very quickly show you the code. So like I almost always do, I read in the number of cases and then I loop through each case, calling a function that solves each case. I ignore. So what does this do? So what's going on? So the input would look like, 2, and then there's going to be some string. And then there might be another string, some characters and spaces, whatever. Okay, and there'll be new line at the end of each line. So the first thing to realize is that you cannot read it with each of these string with something like this because there's spaces, right? So that doesn't work because it will stop at the first space. So you got to use getLine. That will read the whole string from the start to the end of line. However, when you read this and, it will read the 2, and the next thing to read will be right here, the new line character. So I'm going to use C and .ignore to eat that up. So it starts reading from here, and the next time in my solve, it's going to start reading the get line here, and then it will read the rest of the next line. If I don't eat up that new line character after the 2, then the first time I use the get line, it will just read a blank line because it's just going to see the new line right away. It's going to say, I got a blank line. Okay, so this is something that you always have to be a little bit worried about. At least remember that you have to worry about it when you read something with the arrow. We read in an integer with an arrow, but then the next thing that you're going to do is to start using getLine. You got to make sure that you move your cursor to the next where you want to start, assuming that you want to start on the next line. Okay, so now let's see what we actually do in this case. So we read the line. The total is going to count the number of steps I take. For every character, and I start at 1 because I'm always going to be looking at each character and the previous one. There is no previous one from the first step because I'm just starting there. So I start at step 1. I look at where I am from the step before. I look at where I am now. And then the steps, it's either this is one way or this is the other way. So I take P1 minus P2 or P2 minus P1 mod 28. Now, the reason why I do the plus 28, it's exactly when you have something like 4 minus 23, right? This will give you minus 19. And if you do minus 19 mod 28, it may give you minus 19 or it may give you 9. In the C++ standards, it's not specified which one it gives you. Depending on compiler, machine, or whatever, it can give you either one of those. However, if I were to force it by adding 28, that will make sure that I am going to be positive, or at least non-negative, and then the results will always be what I want. So this is a trick that if you have to worry about potential negative numbers when you do a mod, add the mod to force it to be non-negative. Otherwise, your result might be wrong. Okay. All right. Now I have this function called index that I haven't shown you yet, but basically index would take a character A to Z and space and quote and give you a number from 0 to 28, 0 to 27, sorry. And now that you have figured out the number of steps, I do what I told you, compute pi. I compute pi, which is arc cos minus 1. Circumference is 60 times pi. Distance is circumference divided by 28 times the total number of steps. So each step is circumference divided by 28 and then times the total number of steps I take. And then time is distance divided by 15. So distance divided by speed. But I have to remember that each time I pick up a letter in the problem statement, I have to spend 1 second. So every single character in this length of the string counts for another second. After that, I print it out. And this is how you print out a floating point number in fixed decimal notation with 10 decimal places. Okay, and then how do I do this index? So the index, I take a character, I use is alpha to see if it's an alphabetic character. If it is, it must be uppercase A to Z. So C minus A would give me 0 to 25, depending on where I get A to Z. If it's a space, then I put 26. And then the only other case, if I want to be really safe, I should check if it's a single quotation, and if not, I don't know, crash or something. But in the case of programming context problems, you know that the input always follow what they tell you. So I'm just going to return 27 for the single quote. Okay, so this is I don't think that it's extremely easy, but once you know what you're supposed to do, it's a good practice for something that I would say if it's in a regional contest, probably like the second, maybe the third easiest problem in the set. And those are the problems that I think everybody that wants to try the regional contest or should practice to try to get these quickly. Because there's not a lot of very deep algorithmic concepts here. If you practice problems like this, you will be a better coder as well, even for more mundane things. All right, so that's the first problem. Second problem is broken calculator. This is not really that interesting other than you have to read the problem. So you have a calculator that does things in a funny way. So when it says add numbers, it adds the two numbers entered, but also subtracts the result from the previous operation. So immediately you have to know that you probably need to store what was the result from the previous step. Right? When it subtracts the two numbers entered and then multiplies the result from the previous one. When it performs a multiplication, it squares the answer after multiplying the two numbers entered. So it's a little bit strange. And then when it performs division, it divides the first number by 2 if it's even. Otherwise, it adds 1 to the first number and divides by 2. So you can implement exactly like this with if then else, but you can say, well, that's actually just division by 2 rounding up. Whichever way you want to do it, doesn't matter. You also notice that when the calculator is turned on, the previous operation result is set to 1. So initialize it to 1, and then every time you do an operation, just make sure you update the previous results. And then they tell you that the answer that you have to deal with, it's never bigger than 10 to the 18. And that's actually means that it will fit in a 64-bit integer. The input would just be a bunch of numbers, A followed by an operator followed by B, separated by a single space. So like this. Okay, so basically you just have to implement exactly what they tell you. There's not really much more for me to say. So I'll just jump right into the code. And it's the number of operations you have to do. I use long because they tell you that it's up to 10 to the 18. Initialize the previous operation result to be 1. Then for each of the endings, I read in the 2 operands and operation. And then I switch on the operation, right? So if it's plus, then it's the 2 operand minus the previous result. If it's minus, then it's A minus B times the previous result. Times is A times B and then square, or I can just write it like this, A times, because there's no real square operator in C++, so I just write it like this. And then divide is, as I said, you can use the if statement that they basically tells you if it's even, divide by 2, otherwise add 1 and divide by 2. Or you can make use of the fact that when you add 1 and divide by 2 anyway, this is integer division, so if A is even, then the plus 1 doesn't actually do anything because it gets the fraction that you added gets chopped off. But anyway, you can write an if statement if you wish, doesn't really matter. In any case, you do one of these 4 operations, you print the answer, and then you set the previous result to the answer that you just compute. Okay, so that maybe this should have been problem 1 in the set. In any case, this is just hopefully a warm-up question. Okay, incognito. You have a bunch of attributes, you know, what kind of hats they wear, what kind of blah, 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 blah. So each attribute has the name of the attribute and also the category. And you have to figure out how many different combinations of these attributes can somebody have. So for example, here, you have 3 different attributes. You have hats and turban, they're both headgear. And then you have sunglasses, which are eyewear. So you can decide to choose one of the headgear, not both. You can decide to choose one of the one of the eyewears. You can choose one headgear and one eyewear. You can choose only headgear, no eyewear. You can choose only one eyewear and no headgear, but you're not allowed to choose nothing because then there'll be no disguise. Okay, so that's the question. And you have to count how many different ways, how many different combinations of these things can you have. Okay, so this is a combinatorics questions. And basically, you're going to have a bunch of categories, category 1, category 2, up to category whatever, K categories. Each one you might have, so each of the categories will have at least one thing, but maybe you have one attribute 1, there may be 2 things, and this one has 1 attribute, and this one has 3 attributes, and so on. And let's just say for now, we'll just have 3 categories. And the question is, how many different sets of disguise can you have? Well, basically, you have to say, how many ways can you choose a category 1? Right? How many different disguise can you choose? Well, you can choose 2 different things, but you can also decide to choose nothing. Category 2, there's only one choice, or nothing. And category 3, there's 3 choices. You can choose one of the 3 and or nothing. So basically, each category, you count how many things are in the category, and the number of ways you can choose something from this category or nothing is exactly the number of attributes in that category plus 1. So the total number of ways you can do this, it's basically, in this case, 3 times 2 times 4, which is 18. And this would take into account whether you choose multiple categories or some category decide you don't choose anything at all because we have the plus 1. Now, if you're careful in thinking about what's going on, you will realize that this is not right because I allow for the possibility of choosing nothing from every single category. Okay, so that's not allowed. And that's the only thing that's not allowed. And there's only one way to do it, by choosing nothing from every category. So the answer is this minus the empty combination. So the answer is actually 17 here. So at the end of the day, what we have to do is we have to collect things into categories, count up how many attributes are in each category, add 1 to them, multiply them all, and then subtract 1 from the answer. Okay? That's what you have to do. Now, when you multiply a lot of things together, you have to worry about, am I going to have to run out into overflow? So you have to look at the problems and say, can I run into overflow? What is the size of the problems? You have a bunch of test cases, that doesn't matter. What happens in each test case, that's the problem. There are at most 30 attributes. So what is the worst case, right? If all of the things are in the same category, then it's just 30. Then it's just one category 30 times. It's basically just 30 times that there's only 130. That's it. 30, so it's not very big. Things gets big when you have many categories because you multiply a lot of things together. So the worst possible situation is when you have 30 categories, each with exactly one thing. And in that case, you'd be multiplying 2 by itself 30 times. So it's 2 to the 30. But that's okay, because 2 to the 30 is still less than a 32-bit integer, which has the maximum value of 2 to the 31 minus 1. So they picked the 30 carefully. Usually when you see things like 30, 64, whatever, 10 to the 18, 10 to the 9, it's sort of an indication of whether it's, limits of 32-bit or 64-bit integers. Okay, so anyway, so the problem is basically to collect things into categories and then count. So it's always attributes and then category. You don't even care what the attributes are, then you can throw them away. You only care about these categories because you're going to identify 2 headgear and 1 eyewear. That's all you care about. So we're going to use a map of string to integers, which counts the frequency of the strings. Okay, so once again, I do the similar thing. I read a number of cases, then I loop through that many times, each time calling the solve function. Solve deals with one case at a time. I use the frequency, which takes the category names and count how many there are. So I read in the number of number of attributes, and here I just, for each one, read in the name and the category. I throw the name away, and then the frequency of the category, I just increment by 1. Okay, so that this loop will count how many times I see each thing. Now I'm going to multiply all the categories by the counts plus 1. Right, so this goes through the map. Remember that the entry in the map is the key and the value. I don't actually care about the key anymore. So, but anyway, I have to grab it. It's a way to easily go through all the key and values of the map, and then for each value, I add 1 to it, and then I multiply into my running multiplier, and then at the end, I subtract 1 because I have to get rid of the empty combination. Okay, so that's this problem. Let me just pause the recordings. Okay, fourth problem looks maybe a bit scary if you've never seen this type of stuff before. But basically they describe these things called infinite tetration, which are basically chains of exponentiations. And then given particular number n, you want to know if what value of a, if you exponentiate by self infinite number of times, gives you n. Okay, so there's a bit of things to pick apart. At the end of the day, that when you actually write the program turns out extremely short, but maybe it's not so clear what you're supposed to do. So the first thing that you have to figure out is just to start from the basics. If you have an exponentiation like this, a to the b to the c, what does that actually mean? Does that mean a raised to the power b and then raised to the power c? Or does that mean a raised to the power of b raised to the c? So which way do you do first? Do you raise the base first and then the next exponent and so on? Right? Or do you raise the exponent and then once you get the new exponent, then you take a raised to that? Okay, so I'm not quite sure exactly where you would learn this, if you would learn this at all. I guess the answer. So I'm kind of just going to tell you that this is the way to think about it. So you raise the exponent first, and then when you figure out what the value of the exponent is, then you raise a to that exponent. Maybe a minor justification of why it's not this, because this, by the rule of exponent, can be written easily as this instead. So you could have just, if this is what it meant, then you could have just write something like this instead of the more complicated chain of tau exponents. Okay, so that's the first thing, is to figure out what a to the b to the c means. So now if you have a to the a like this, what you're supposed to do is to first figure out what this is. And then when you get the answer, then you take a raised to the exponent, right? So whatever that is. But remember, we call this a with a little infinity um, thing on the right, on the left, right? So this is a to the little infinity on the left. They call it tetration. It's a raised to the power a, dot, 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 forever. And now you look carefully. I said that a raised to the power of a is forever. It's the same as first computing what's in the exponent and then taking that answer and raise a to it. But if you look at what's here carefully, it looks awfully like this. Well, actually, it looks exactly like this. So actually, you have this relationship that this tetration, whatever the answer is, it's equals to a raised to the value of the tetration. It's a little bit strange, but that's what it is. So when you see these infinite chains of sequences, then what you do is you try to pick off one of them. So in this case, pick up one of them, and now you still have this infinite sequence of stuff. And then if you can recognize this being the same thing as you had before, so in a recursive way, it's actually not recursion, because in this case, it's actually exactly the same thing. You're not reducing it to something smaller. But if you see that it's exactly the same thing, then you get this. So we have this equation now. So now you're given that the value of the tetration is n. So they give you n, and you ask what value of a makes it work. So when you plug this in, it's just n. It's equals to a raised to the power of n. N is known, a is unknown. So you just take the both sides to the 1 over n power. So a to the n 1 over n, and this cancels out, and you just get a. So the answer is simply taking n to the power 1 over n, or taking the n's with a n. And that's it. That's the answer. Okay, so I mean, it takes a bit of thinking and maybe recognize, if you have seen this type of stuff before, this kind of trick to realize that this is what you end up with. Once you have this equation, if you get to this part, then it's pretty straightforward to actually solve it, right? Because you just have to write the code to compute n raised to the power 1 over n, which is exactly what I do. Right, so the code is actually really simple. Double n, read in n, and then a is just power of n to the 1 over n power. So it's a pretty scary looking problem, but the solution was surprisingly easy once you figure out what to do. All right. Now, last problem is a bit complicated. I don't necessarily want to show you the code. You can always find it on my GitHub. I want to kind of go through sort of an explanation of what this is about and maybe explain the algorithm and then the code. If you were interested, you can look at it. Okay, so you have a bunch of boxes, and I believe there are up to 1,000 boxes. Each box may or may not have the bird in it. Okay, so you don't know. So there's one bird, you don't know which box it is in. But each box has a certain probability, P1, P2, of the bird being in there, right? So P1 might be 0.25. So if you open this box, there's a 25% chance that it might be in there, and so on. And they all add up to 1. So you know that the bird is in one of these boxes, you just don't know which one. And then it's fixed. So you can't like open box 1 and then put it back down and then open box 3 and then the bird escape to box 1 again. No. If you open box 1 and box 3 like this, for example, if you open these two boxes, then you got 35% chance that you will see the bird. Okay, so the first thing to realize is that if you open a bunch of boxes, the chance of any one of those boxes being correct is just the sum of them, right? So why is it the sum? Because it's the probability of the bird being either in box 1 or box 3. And if you have more, if you're trying to open box 1, box 3, box 7, whatever, then it's more of these. And just basic probability is the probability box 1 plus the probability box 3 minus the probability that both of these events can be correct at the same time. But in this problem, there's only one bird. It cannot be in two boxes at the same time. So this is 0. You can ignore that. In other words, you only have to worry when you want to open a bunch of boxes and you want to know what's the probability that you will see the bird in any one of the boxes, you just have to add up the probabilities. Okay, so that's the first part of the problem to think about. You just add the probabilities. And you have a certain, whatever letter they use, P, capital P. Okay, you want to make sure, so if capital P is like 0.5, then you want to be 50% sure, at least 50% sure that you'll see the bird. So what you want to do is you want to open enough boxes so that the sum of probability is at least 50 or 0.5. Okay, now, if this is the only thing there is, then it's relatively simple. You take the most probable boxes and you add them up until you're bigger than the probability, bigger than equal to the probability you're given, and then you're done. That will make sure that you open the fewest boxes possible. However, there's a second number called energy, because some boxes may take more energy to open. So even though this has 25% chance of being the right one, maybe it takes 10 unit of energy to open because it's really heavy. But this one only has 10% chance, but maybe it only has, maybe it's very light. So then you have to say, well, maybe I open 5 light boxes that adds up to 0.5 as opposed to one really heavy one that gives me the right thing. So that's where the tricky part comes from. that you have this energy of how heavy you are, how heavy the boxes are. So the other thing that's hidden in the problem statement, if you read it carefully, is that all probabilities are between 0 and 1, of course, all as always, but they will always give you 4 decimal places. It's always between 0.00. So even though it's you can, I guess you can say it's a double, it is really not a double. It is actually, if you think about it, it's actually a number between 0 to 10,000 if you count by 0.0001. And you can actually convert all the numbers to integers. Why? Because we prefer to deal with integers if we can, but there's actually a very important reason. Whatever p is, so p is 5.5, then p is really 5,000 because we are going to convert it to integer. We convert all of these to integers, and we're looking for a bunch of boxes that will add up to a p-value of at least 5,000. And out of all of those, I want to make sure that I choose the lightest set of boxes. Okay, so for those of you that have seen this type of problem, it goes under many different names, but this is a very standard problem called knapsack. And in the knapsack problem, you have a knapsack, okay, of a certain capacity, and you have items that have a certain weight. So item that have weight, how heavy it is, and the value, like how important it is to you to take it. So your knapsack can hold, I don't know, 5,000 grams of stuff, and each item has a certain amount of certain weights, and each has a certain value, and you want to bring as much, you want to bring a bunch of items that have the highest total value while being able to fit the capacity in the backpack. So this is a little bit, it's similar, but slightly different because capacity for knapsack, you want to pick things that are no more than 5,000. Over here, we want to take things that are at least 5,000. So if we think of the probability as the weight and how much we want as the capacity, we're actually going the opposite way. Also, in the knapsack problem, you're trying to maximize the values of the things taken, whereas we're trying to minimize the energy that I take. But the same algorithm works. It's just that instead of max, you take min and so on. Otherwise, it's really the same algorithm. Okay, so if you haven't seen this algorithm, let me explain how that goes, and then you can look up the code. There are many different ways you can implement this, but now that I've used the word knapsack, you can also look up many tutorials if you want. So anyway, so I have a bunch of boxes. Each one has a probability, Pi, and I have an energy, EI. I want to pick a subset of boxes, so each box can be used at most once, so that the sum of the PIs that I choose is at least capital P, and the sum of the EIs that I choose, it's minimum. Okay? And I'm going to assume that all of these are integers from 0 to 10,000, right? So I'm converting everything. So the other probabilities are between 0 and 10,000, and I think the energy is between 0 and 1,000, but that's not too important. The energy is not the important part. What I'm going to do is I'm going to ask. I'm going to write a function called f. It has 2 parameters. So I'll call it probability. And let's call it m. What is this? Okay, so I'm going to have box 0, box 1, up to box n minus 1, right? This is going to be the minimum energy needed to open boxes 0, 1, 2, up to m. So the m, it tells me which boxes I'm allowed to consider. If m is 0, I'm only allowed to consider the first box. If m is 3, then I'm allowed to consider 0, 1, 2, 3. And as I increase m, I will consider more and more boxes. Okay, so the minimum energy needed to open boxes 0 through m, open some of the boxes, because I don't have to open all of them, to get exactly, actually, okay, I don't mind. Let's not use probability. Let's call it capital Q. Total probability Q. Okay, so I want to be able to exactly hit probability Q. And if it's not possible to hit exactly probability Q, then f of qm, it's some really big number, which I'll just call it capital infinity. So it's just so big that you will never want to do it because I'm trying to minimize energy, right? Okay, so I have this function. So so basically what I want to compute, if I know how to compute if I know how to compute this function with all possible parameters, what I want is f of n minus 1, because I want to be able to look at all the boxes. And what probability do I want? Do I want p because I want to be able to open enough for probability p? No, because it's asking me to do exactly p, whereas the problem says at least p is good enough. So what I have to do is actually have to compute all of these for increasing p all the way up to 10,000. That's the maximum possible. And of all of those, find the minimum. So if your p is 5,000, maybe there's no way to get exactly 5,000, but maybe there's a way to get 5,001. And maybe there's a cheaper way to get 5,002, and so on. Right? So among all the things that gets you at least capital P, you want to take the one that's the minimum. And if you have any that's not possible, because we set them to be infinity, you'll never choose them. Why? Because you can always open all of them for a finite amount of energy and have probability 1. Okay. Okay, so that's the first thing, is that if you know how to compute this magical FQM, then you just look up f for Pn minus 1, f for P plus 1, n minus 1, and so on, and pick the minimum. So the next question is, how do you compute this? Okay, so get rid of some of these things. So the easiest thing to do is do some base cases. Okay, so base case when one of the parameters is smallest. So, when m is 0, that means you're only allowed to open the first box. If you're only allowed to look at the first box, then the cost to open to get probability 0 is just not to do anything. You don't need to open anything. You get 0. That's it. Otherwise, the cost to get exactly the probability of the first box, it's exactly the probability that the energy of the first box. And then any other probability uh, any other q, it's infinity for all q that is not 0 and not p0. Okay, so basically, if you only have one box, either you open it or you don't. Now, what if m is greater than 0? So now you have more boxes. Well, just because you have that one box doesn't mean that you have to use it. So you can decide not to open it. So if you don't open that box M, then it's basically like, what's the best way you can make the same probability without using that box? So you can pretend that the box M never exists. And this is basically don't open box M. Well, okay, so if you don't open box M, that's the cost. Otherwise, you open box M. That's the other choice. So what do? You open box M, so it's energy M. You have to open it. And then, if you're looking at Q is, I don't know, 0.5, 5,000 and box M, it's 1,000, then you want to make 4,000, right? So if Q was, let's say 5,000 and box M, so P of M, it's 1,000, then you're saying, okay, if I wanted to make 5,000 and I want to use box M, then we want to be, that means that the remaining other boxes, I still need to make 4,000. So basically I'm saying, right, with the first M minus 1 boxes, I need to make exactly Q minus PM. So either I open box M or I don't. Which way do I do it? Well, I don't know. Whichever one is minimum. So I compute both of them, whichever one is minimum, that's the one I choose. And again, either one of these could be infinity. And well, both of these could be infinity, meaning that it cannot be done. Now, there's one little thing here that you have to be a bit careful about here. Q minus PM. It could be that you're trying to make, I don't know, 500, but the box that you're trying to open is 1,000. What do you do? Right? In the case when you're trying to make a negative amount with anything, so this is another base case that maybe we haven't thought about yet. Well, actually, you don't have to do anything. If you already had too much, that means you don't have to open anymore. Actually, similarly, same thing here. If it's not just with 0 box, if you want to make nothing, doesn't matter how many boxes you have. If you want to make nothing or negative things, that means you're already done. So it's the answer is 0. So those are the base cases. So you can actually write this recursively, right? So these are your base cases. I guess these are your base cases. And if you're not any one of these cases, you recursively compute these two, pick the smallest one, and return. Now, remember that this value is between 0 and 1,000, 10,000, and this is at most 999. So altogether, this is 10 to the 4, this is 10 to the 3, at most 10 to the 7 different combinations of first and second parameter you can use, which is not that much, it's 10 million. But if you do things not in a very optimized way and you just write the recursion, you're going to be in the same, you might know that if you do the simple Fibonacci numbers, right? F of n is equals to f of n minus 1 plus f of n minus 2, and then f of 0 and f of 1 is 1 kind of thing like this. And you implement this Fibonacci sequence computation recursively without actually doing any things smart, just writing a recursive way, it's going to take forever because it's going to recompute the same thing over and over again. So what you have to do is use dynamic programming, right? So to recognize that even though you could be trying to compute the same thing recursively, many things over and over again, there are really only 10 million different things they can ask you. So you have to use dynamic programming, which means that you have to have a table of the 10, basically 10 million combinations of the Q and M. Every time you ask, you're computing Q and M, F of Q and M, you ask, have I seen this combination of Q and M before? If I have not, I got to compute it. But after you compute it, you store it in a table, okay, so that you don't forget. The next time you get asked the same Q and M, you look it up and you say, oh, I've seen this before. Here's the answer. I'm not going to recurse. And that's how you make it faster. Now, there are many ways you can do this computation. If you go and look at my code, I would do it in a slightly more optimized way because you'll realize that each row, so when M is whatever value M is, it only needs to refer to M minus 1 and not M minus 2. So I can basically keep track of, so this is Q and this is M, right? So this is M is 0. To compute M at 1, I need to refer to things on 0. And when I compute 2, I need to only refer to the column at 1. And when I refer to column at 1, that means I don't need to actually keep track of this column. So I actually only need to keep track of 2 columns at a time. I can get rid of the column that's 2, 0. So I don't actually need a 2-dimensional table. I only need two 1-dimensional tables. But actually, if you read my code, I don't even keep 2 things. I keep only 1 thing. And that's because I realize that when you're computing something here, so so in 2 rows of, I'll start 2 columns of this. If I'm computing something here, I always refer to this thing and this something that's smaller, Q that is either itself or smaller. You will never go this way. So what that means, if you're really clever, is that when you're computing this entry, you know that you only have to refer to these 2. So once you compute a real number, or the new number, you can just replace it. You can just put it here. These are the new entries. These are the old entries. Because once you replace this, when you compute this, you'll never try to look at these again. So you're not going to end up sort of looking at the wrong values when you update things in this way from biggest to smallest Q. Okay, so I did some kind of clever tricks so that I only have to remember one single column in this table. Okay, it doesn't actually matter because 10 million is not really that much. You can afford to use 10 million entries, but the way I wrote it, it's just sort of optimization to avoid that. Okay. Other things you have to be a little bit concerned about. What the heck is infinity? How do you represent it? Right? Because if you choose something that's too big, right? So okay, so this is a really weird way to say it. How can you choose an infinity that's too big? Right? So you need to choose an infinity that's big enough. Otherwise, uh, some of these answers that you compute might be bigger than infinity. That's no good. But how can infinity be too big? Because, for example, when this comes back, and let's say this returns an infinity, whatever you did choose this to be, you're going to take this number and add it. And if infinity is the maximum integer that you can store, then adding this will be overflow. So exactly what we mean by infinity, it's a little bit, you have to be very careful. You can, if you want, just, if made, I don't know, use -1 to represent infinity. And then every time something returns before you add it to E of M, check if it's -1 before you do it, or whatever you choose to use to represent infinity. Doesn't matter. But the way I wrote it here is nice mathematically, but there's no such thing as infinity in a computer program. So you have to be very careful what you really mean. Um, so I do use ins max for my infinity, but then uh, when it comes back, I check to make sure that if it's infinity, I don't try to add it. I just I just don't add it. Okay. And then I only use one dimensional array because I told you that if I go in a correct direction, I can get away with storing only one. But anyway, it doesn't matter. You can use two. And I didn't write it in a recursive way. I wrote it in the iterative way, making sure that every time I look at a column in my table, the previous column has been computed, etc., etc. Okay, but that's not exactly how I implement is not important. The important is to going through this process and understanding the recursive thinking and then dynamic program. Okay, so that goes to, so certainly the last problem, it's something that I would consider more advanced. I would probably think that probably in the problem sets in the regional contest in, I don't know, with let's say 10 problems, this would probably be the fifth or sixth hardest problem in the set. That's my guess. It's something that if you're not familiar with comparative programming algorithms, that this is definitely new to you. If you've taken 3620, this is something that you should have learned, but maybe you haven't really tried solving problems or implementing it. But people that are practicing a lot for comparative programming, this should be something that fairly straightforward. Not to say that it should be straightforward for you now, but if you keep practicing and trying these problems and then program a few of these to get used to the thinking, then hopefully you also get there by the time the regional contest comes around. Okay, so that's it for this week. And I'll post another set tomorrow. Okay, see you later.